Let's do another one. A small immersion heater is rated 550 watt. Now, what is a watt? A watt means joules per second. You have done that in Physics 1, the unit of power. So what is the meaning that an immersion heater is rated 550 watt? It means that immersion heater will produce 550 joules of heat energy every second. That is the meaning there. It produces 550 joules of heat energy every second. Now, what's the question? How long will it take to heat 200 grams of water from 20 degrees Celsius to 100 degrees Celsius, assuming that 90% of the heat produced by the heater is used in heating water? Alright, how do we start this problem? Since we need to find the length of time it takes to do this heating, let's start by saying that let the time be t. But first understand the meaning of the given statement. The heater is rated at 550 watt means that it supplies 550 joules of energy, which is heat energy here, to the water every second. Let the time taken to heat the water be t seconds. Alright? If 550 joules of energy are produced in 1 second, what is the amount of heat energy produced in t seconds? It will be 550 times t. Is that right? So the amount of heat energy supplied by the heater is 550 t joules. Now, are all this amount gone to heating water? No. Only 90% of this is used in heating water. The rest is lost to the surroundings. Well, there are many ways heat can get lost to the surroundings. Now, does it mean that the conservation of energy is not obeyed? Well, it is obeyed. All that heat is taken into account. Alright, 90% of this heat is used in heating water, and therefore the amount of heat Q used in heating water is 90% of this, which is 0.9 multiplied by 550 T. That will be 495 T. Now, this is the amount of heat supplied to water. Now, this heat is used by water to increase its temperature from 20 degrees Celsius to 100 degrees Celsius. Now, what is the formula for the amount of heat used in raising the temperature by an amount delta theta? It is mc delta theta. So this quantity will be equal to mc delta theta, where m is 200 grams, c is the specific heat of water we know, delta theta is 100 minus 20. Alright, so the amount of heat energy needed to heat 200 grams of water from 20 degrees Celsius to 100 degrees Celsius is Q equal to mc delta theta. And that will be, mass is 0.2 kilogram, specific heat of water is 4180 joules per kilogram per Kelvin, and the change in temperature is 80 Kelvin, and that will be 66,880 joules. And what is this equal to? Where does this come from? From this quantity. So 495 T equal to this quantity, and therefore T equal to 135 seconds. That is 2.15 minutes. Okay? You must be very thorough with these kind of problems. Alright. Let's now talk about internal energy of an ideal gas. We have been discussing ideal gas for some time. Internal energy of an ideal gas. Now, let me see if you remember, in lesson 2.1, we obtained an expression for the kinetic energy K of n moles of an ideal gas. Now remember, we obtained that using the assumptions that we made in that lesson. You remember we made 4 assumptions of the kinetic theory for gases. And using that assumption, we obtained an expression for the kinetic energy K of n moles of an ideal gas. Now, how many of you remember that relation? K equal to 3 over 2 nRT. Is that right? Yes. K equal to 3 over 2 nRT. In fact, when there is no change in potential energy, and that is the case in the case of a certain amount of gas. You see, when you supply heat to a gas, the increase in internal energy is purely increase in the translational energy of its molecules. So all the internal energy increase is translational energy or the kinetic energy, which results in an increase in temperature. So the internal energy of n moles of a gas at a temperature T is K equal to 3 over 2 nRT. Remember, this is a theoretical value. We can now subject that to experimental scrutiny to make sure that we are in the right track. So we will use this as we go on. For an ideal gas at low density, its internal energy depends only on the temperature, right? Its internal energy depends only on the temperature. This is because at low densities, the intermolecular forces can be neglected. At low densities, gas molecules are completely free. There is no potential energy at all. Now, thus the internal energy of a gas is just the translational kinetic energy of its molecules given by U equal to 3 over 2 nRT. In other words, the internal energy, all the internal energy is due to the internal kinetic energy, and therefore the internal energy U equal to 3 over 2 nRT. You cannot forget that. I'm going to ask you that again and again as we go on. Let's now talk about work and the PV diagram for a gas. Work and the PV diagram. Now, do you remember in Physics 1 when we talked about work done by force? We said work done by a force is the area under the force displacement graph or force displacement diagram. Well, I'm sure you remember that because work done is force multiplied by displacement. And if force does not remain a constant, then work done can be measured as the area enclosed by the graph of force against the displacement. In the same way, we can relate work done by a gas related to the pressure against volume graph or pressure against volume diagram. Now the figure on the right shows an ideal gas enclosed in a cylinder with a tightly fitting piston. Alright? The pressure of the gas, this is the gas inside, this is the piston. The piston can move back and forth. Now, the pressure of the gas is P and the volume is V. And the area of the piston is A. Now, if the pressure is P and if the area of the piston is A, what is the total force pushing the piston outward, that F will be equal to pressure multiplied by area. Is that right? The thrust, the total force is pressure multiplied by the area. So if the area of the piston is A, the force exerted by the gas on the piston will be F equal to P times A. And now, if this F displaces the piston through a small distance dx, what is the work done by that force? If the piston moves through a small distance dx, then the work done dW is given by dW equal to force multiplied by the displacement. Is that right? Work done is force multiplied by the displacement. So the force is P times A. Now I hope you can understand that concept, that the piston has an area A and the total force on the piston is P times A. Now consider this as the piston. You see, doesn't it look like a piston? And this is the area A. The pressure on it is P. So the total force on this area is pressure multiplied by the area. And if that force produces a small displacement dx, then the work done will be that force multiplied by dx. Alright. Now, that can be written as P times the, now, force is P times A. So I'm going to replace this force by P times A. And you notice I colored that A times dx. A times dx. Suppose this is A and this is dx. What is A multiplied by dx give you? If you notice, this is a disk. The face area multiplied by the thickness will be the volume. But in this case, what happened is that piston is moving through a small distance dx. That means A times dx here is the increase in volume. Is that right? A times dx is the increase in volume over here. This is A times dx, and that is equal to dV, the change in volume. Therefore, we can say the small work done equal to PdV. You see, when this force produces a small displacement dx on the piston, the work done during that time is pressure times the change in volume. Always remember, work is done only when the volume changes, because there has been a displacement. Now, the total work done when the volume changes from V1 to V2, if the initial volume is V1 and the final volume is V2, then the total work done will be given by an integral. Why do we have to integrate? Because as the volume increases, the pressure will change, the force will change. The force does not remain a constant. And that is why we got to go in very small steps of displacement dx. And then we integrate this whole quantity from V equal to V1 to V equal to V2. So the total work done is now given by integral V1 to V2 PdV. A very important relation, we would want to use it again. So the small work done when the displacement is very small is PdV, where dV is the change in volume. And if the volume changes from a value V1 to V2, the total work done will be W equal to